Good morning. My apologies for the delay. Here we go. Hopefully everyone's okay with those crazy storms. Yeah, just nuts. All right. So today what I want to do is I want to introduce what we call a chi-squared test. And so we're going to do section 6.3 and the same goes for 6.4. So we'll see how deep into 6.4 we go. Otherwise, I might just leave that for you to read up on, but it's the same. It's just with more than a one-way table. Okay, so hey, Emily, what's a one-way table? What's a two-way table? We'll get there. All right, so 6.3. And let me just make sure, okay, is goodness of fit testing, which sounds funny, and it is funny to call it goodness of fit. But I don't know what else we would call it, and so that's what it's called. And it's called goodness of fit testing. Goodness of fit testing with chi-squared. So chi is a Greek letter chi, and it kind of looks like this fancy X and squared, and we read it as well, it's technically chi squared, but this, you can read it as how do you phonetically say it? Chi. Okay, so there's no ch in there, it's just k. Otherwise you'll sound like you don't know what you're talking about, and I don't want that. So you have to say chi, okay? So goodness of fit testing with chi-squared. Okay. So usually I just do kind of a capital script X, and then and that's chi. I'm not sure I'm doing it correct. Anyways, close enough. So it's just this kind of script X, and you can write chi-squared like this if you want, but I'm lazy. So so last week, if you can remember that far back, because I think we saw each other a week ago, what did we do? I feel like we finished two proportions and the difference between two proportions, right? And so we wrapped up, and I feel like we finished it. I hope so, I can't remember. We talked about the difference in two proportions, right? So we talked about how do we analyze one proportion, and maybe, you know what? Maybe what I'll do is, just for a little bit of review, not much. About 3 lines of review I'll leave myself. But in terms of review, right, we analyzed a single proportion against some hypothesized proportion, right? So we analyzed a single proportion against a hypothesized proportion. Okay. And then what we did was we extended that, and we said, and there were lots of things we could do. We could do a hypothesis test, we can do a confidence interval. We even looked at finding the sample size, right? So a hypothesis test, confidence interval, calculate n, right? So we've looked at a single proportion, and we did a bunch of stuff, and we used it to introduce the ideas around hypothesis testing and confidence intervals, especially. And then we said, okay, well, what if I have two proportions, right? What if I have two samples that I want to compare? Okay, and so we analyzed we analyzed the difference in two proportions, right? And so you can think of them as being compared to each other, but technically what we're doing is we're looking at the difference, and is that difference significantly different from zero? So context tells you what the difference is coming from, right? I say difference there a lot, right? The difference as in P1 hat minus P2 hat versus are they different from each other? That's all from last week. So we analyzed the difference in two proportions. Goodness of fit testing extends this so that we can look at more than just two proportions, right? So we can look at one proportion. How does it compare to some hypothesized value, right? That's great. We can compare two proportions, but what if what if we have some categorical variable with 4 categories, right? And I have some idea of the distribution among those categories. Okay, so goodness of fit testing. Now we extend our analyses to more than 2 proportions. Okay. So if we consider a categorical variable, because for proportions we have categorical variables, right? So proportions equals categorical variable. I guess I should say categories of a categorical variable, technically. So now consider a categorical variable with more than 2 categories. Okay. So now we consider more than 2 categories. Okay. So what's going to happen is we're going to have some sample distribution, okay? And so some count is going to be in each category, okay? And so, and then we're also going to have some hypothesized, or we're going to start calling it expected number of counts or proportions in each of those cells, right? And so the cells correspond to the category. So for example, if I have category 1, category 2, and category 3, what's going to happen is I have some observed count. Oops, that doesn't look like observed. Observed count. And then we're also going to have some expected count. Okay. In general, when you can lay out your information like this, right? So now notice that we're talking about the counts. Okay. And so we're not talking about the proportions anymore, which is weird, but it makes it a little bit easier too, right? So, so we're talking about the counts. So that's important to keep in mind. But notice how we have binned data, right? And so here we have binned data. I only mention that because the textbook is really adamant about calling it bin data. And the reason for that is because you could take a numerical variable and create categories, right? You could take some reported income and put them into income categories, right? And so as soon as we're able to develop these bins, then we can apply a chi-squared. So what's going to happen is we have these observed counts, right? How many are in category 1, how many are category 2, and how many are in category 3. Okay? Then the expected count is going to come from our null hypothesis. It's going to come from, what did I expect to see here? Did I expect to see an even spread among each of the 3 categories, right? Did I expect to see a third and a third and a third of the counts in each category, right? Or did I expect maybe a 50, 20, 30 split, right? And so we've got this idea about the hypothesized distribution. Okay. So then here, the expected count, this becomes the hypothesized distribution. Hypothesized distribution. Yeah. So what we're going to use to denote each of these counts is we're going to use a capital O, which can get confusing, right? We don't like to use O because it looks like 0, but here with context, because we're going to have a little subscript on there, it should be obvious that it's not a 0, right? But you want to have those little subscripts on there. So the observed count, we're going to denote by O1, O2, and O3. Okay. The expected count, well, we're going to denote by E, capital E, so E1, E2, and E3. Okay. Now, the reason I'm mentioning this is because we need this notation to develop our test statistic, which is the chi-squared, okay? And so in general, the chi-squared test can be applied to a lot of different situations. Just like we saw the Z test, right? We can calculate a Z for one proportion compared to some hypothesized value. We can calculate a different type of Z, but it still becomes a Z in the end for the difference of 2 proportions, right? So we can use this Z in different scenarios, and same thing with the chi-squared, and that can be confusing, right? But as soon as you have you have more than 2 categories, right? Or more than 2 proportions that you want to compare to some hypothesized value, then you're going to be using a chi-squared. So in general, your null hypothesis is going to be that the sample came from the hypothesized distribution. And I know that sounds weird because the hypothesized distribution is in the hypothesis, but the sample came from the hypothesized distribution. And the alternative hypothesis is that the sample did not come from the hypothesized distribution, right? So for chi-squared tests, we're going to be writing out our hypotheses. And for me, that always makes it a little bit tricky, right? Because then I have to kind of remember what to say. Whereas if it's just with notation, then I'm kind of guided along that way. But in this case, the alternative hypothesis is that the sample did not come from the hypothesized distribution. Distribution. Okay. notice that there's no one-sided tests anymore, right? You either came from the hypothesized distribution or you didn't come from the hypothesized distribution. And what we're going to see is that the chi-squared really only has one tail. And so that's kind of beyond the scope here, but that's the reason. And for us, we just need to kind of know when to use the chi-squared and how to use it. And I stole one of the questions, but I'm going to keep it a little bit longer before we go through it. I just want to introduce, right, what are some of the building blocks that we need? We need to know the hypothesis, right? We need to know, so we need to know the null hypothesis, which is then going to lead us to the alternative hypothesis, right? So we really only need the null hypothesis. We need to know the test statistic, right? But also we need to know the conditions that have to be met before I can do this test. Okay, so let's talk about the conditions first, and then we'll come back to this. So in order to apply a chi-squared test, okay, we only need to check two things. And honestly, there's only one thing that you're going to have control over. And so in order to apply a chi-squared test, we need to check two conditions. We need to check two conditions. The first one is independence. And that's always going to be one of our conditions, right? Can we assume that each of these counts are independent of each other, right? Did they come into the sample independently? So basically, was the sample randomly selected? That's the only way that we can check that. So independence is each count in the table independent of all the other counts? Right, and so here, really what we're asking is, was the sample randomly selected? Was the sample randomly selected? We've seen that before, right? Sometimes we have to say, I assume the sample was randomly selected, right? And so we have to state that as an assumption. So sometimes we state them as assumptions, but we are just checking the conditions, and then conditions become assumptions if we're not feeling 100% about it. So the second condition, and this is kind of the main one, is the sample size condition, or what did I call it? I had little notes here. I called it the sample size. I'm on a roll here. All right, so the sample size condition. The expected number of counts in each cell has to be more than 5. That's weird, but the reason for that is because we need to be able to detect at least 5 expected successes. If you're trying to detect a really small proportion and the expected count is just 1, then you don't have enough data there. Okay, and so the sample size condition is the most important one, and it says that each cell must have an expected count of at least 5. It can include 5. It's rarely going to be the case that, you know, you're deciding to not do the chi-squared test because you have an expected count that's too small, right? But this is the main one that you need to check. it's always going to be satisfied. It's one of those again, right? And so it's always going to be satisfied, but you have to say it. Right? Okay. So once we've checked the conditions, then we can go ahead and, well, we can state our null and alternative hypotheses either before checking the conditions or after. It doesn't really matter, but I like to get it out of the way before I state them. So I kind of went out of order here, but that's okay. So now what we're going to do is once we have confirmed that the conditions are satisfied, we can continue with the chi-squared test. And I'm going to parking lot this a little bit longer here. We can continue with the chi-squared test. Yeah. All right. So step one, of course, for our hypothesis test, there is no confidence interval. I should say that because we have more than one or two categories. And so what would we build a confidence interval around? I don't even know. Right. And so there is no confidence interval anymore. And that's nice, right? So now we're just going to focus on chi-squared tests. And so step one is to state our hypotheses, which we already did up here to introduce the idea. Now, usually, let's see here, right? Generically, we say that the sample came from this hypothesized distribution. You're going to want to tweak that to apply to this question, right? So the hypothesized distribution could be the groups are independent of each other, meaning they have the same probability of happening, right? Or we have some idea of what population we're drawing from, right? So is the sample representative of the population? And the other one would be if we have some guess at what the distribution is going to be, right? How well does our sample fit in that, fit with that distribution, right? And so this generic hypothesis has to be tweaked to match the question, right? And so here, tweak to match the question. Okay. And same thing with the alternative hypothesis, but we focus on the null hypothesis because the alternative hypothesis is just always going to be the opposite, right? And so this one is always the opposite of the null hypothesis. Okay, and so you would adjust it to the question. All right, so a little bit weird, right? But the same framework applies. So then step two is what? Step two is do the test. Okay, what's the test? Step two, do the test. Move it down. Okay. The textbook does a really thorough job of explaining, you know, why the chi-squared is what it is, and it's rooted in z-scores, right? Because we want to know how far is our observed values from the hypothesized values, right, or our expected values. And so it goes through and it guides you through, but I just want to give it to you. And so hopefully that's okay. But if you're feeling like, whoa, where did that come from? Then the textbook does a really thorough job of just walking you through why it is. But we're just going to jump right into it. So the chi-squared statistic is, and I'm going to write out the sum first, or maybe what I'll do is it's the sum from I equals 1 to k of OI minus EI squared over EI. Okay. That's a little bit nasty, but if we expand this, right, just so you can see what's going on, right, starting at I equals 1, we have observation 1, or the observed count 1, minus the expected count for group 1, right? And then we square that so we get a positive value always, and then we divide by the expected count. Okay. So this is the same as O1 minus E1 squared over E1 plus O2 minus E2 squared over E2 plus dot, 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 up to O2, sorry, okay. Haha, okay. Okay minus EK squared over EK. Okay. So now, right, we have K categories. K categories. Okay. So if I scroll back up, let's see here, to this here, right, what would we do? Well, we would have some observed count in group 1, group 2, group 3, so K would be 3 in this case, right? And so what we would do is we would take the observed minus the expected, square it, divided by the expected, plus the observed minus the expected, square it, divided by the expected, right? And so it's weird, it's different from what we're used to, but as long as you kind of wrap your head around that's what you have to do, then it's not that bad, right? And of course, software will do it for you, but we are going to do it by hand. Of course, you're allowed a calculator. You're insane, right? With a calculator by hand. And so we're going to do these by hand, just so you show me that you know what to do. But then, of course, any software will do it for you too. Okay, so K in this case is 3. Okay. And how do we get these expected counts? Well, if I, for example, say that these categories should be independent of each other, what does that mean? It means that, well, with 3 categories, I should see a third of the counts in category 1, a third of the counts in category 2, a third of the counts in category 3. Okay. And so if I have a sample size of 200, right? So you're going to have a sample size, then I would expect to see 200, and I picked a bad 200 divided by 3. How about I have a sample size of 180? Just to be cheeky, right? 180 times a third is 60, times a third is 60, times a third is 60, right? So I would expect to see 60, 60, 60, right? I'm going to have some observed count, and we all understand that if a sample is randomly selected, then those counts aren't going to be exactly 60, right? That would be some crazy fluke, right? But we expect the observed counts to be hovering around 60, right? Unless there's evidence against the hypothesized distribution, right? So once you have your chi-squared, it's going to, so this is going to be your test statistic. Okay, so the chi-squared, and maybe I'll do green. This is your test statistic. Okay. Just like a z-score has been our test statistic in the past, now we have a chi-squared test statistic. Okay. So we use in step 3, find the p-value. We use the test statistic to find the p-value, right? And so step 3, find the p-value. Okay. We use the test statistic to find the p-value. So just like with a z-test, which means the z is the test statistic, where z is the test statistic. Oops. Okay. We use the test statistic, we use the chi-squared test statistic to find the p-value. We use the chi-squared test statistic to find the p-value. Okay. The problem with the chi-squared, and I wonder if I'm still on the right page here. I was looking at, oh no, I was grabbing that. The problem with chi-squared is it changes shapes dramatically depending on the degrees of freedom. Here. Okay. So the shape of chi-squared depends on just one thing, and that is the degrees of freedom. So we call these, the degrees of freedom is just a way to communicate how many groups we have. Okay, so the shape of chi-squared depends on something called degrees of freedom. And we're going to see degrees of freedom in different contexts, right? So we're going to see this this shape shifting depending on the degrees of freedom later as well with the t-test. Okay, so this is something that we need to get used to. And so the shape of the chi-squared depends on something called the degrees of freedom. The degrees of freedom, which we usually just abbreviate DF, is how we communicate how many groups we have. Oops. How we communicate the number of categories we have. Number of categories we have in our table. Okay. Scoot that down just. We'll get there. Okay. So here, I guess we need to know the degrees of freedom. Hey, I almost jumped there. Okay, that's okay, that's okay. The degrees of freedom is going to be k minus 1. Okay. So the degrees of freedom is the number of k is the number of categories. So it's the number of categories minus 1. Okay. So in this case here, right, and let me just blow it up because I have to be able to see. Hello, there. If we have 2 degrees of freedom, what does that mean? Well, it means we have 3 minus 1, right? So we have 3 categories. So here, this means we have 3 categories. 4 degrees of freedom means we have 5 categories. 9 degrees of freedom means we have 10 categories, right? Boom, 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 boom. We have 10 categories that we want to compare to some hypothesized distribution. So what does this look like? Well, the chi-squared, it always starts at 0. Okay, so it's always going to be a skewed distribution, and it's always going to be skewed to the right. Okay, and so what happens is the chi-squared always starts at 0. And remember how we calculated the chi-squared? We took the observed minus the expected count. So that's where we could get a negative value. But then when we square that, that's how we get rid of that squared or that negative value, because squaring a negative value makes it positive, right? And so, so we're always going to have positive values because we've got a positive divided by the expected number of counts, right? And so that's going to be positive as well. And so here, chi-squared values are always positive. There. Okay. And depending on how many groups you have, right, it's going to change the shape. So here, this looks like an axis, but it's actually not. It goes, it shoots up with 2 degrees of freedom, right? And so that's 3 categories. And then it trails off like this. Okay. So if we increase our degrees of freedom to 4, right? So now we have 5 categories, then the distribution starts to look like this, right? And so chi-squared distributions are always skewed to the right. Chi-squared distributions are always skewed to the right. Okay. But it depends on the degrees of freedom, how skewed it is. Okay. So of course, again, we would use software, and software would just give us the chi-squared value, okay, as well as the p-value. So we would usually use software, right? Probably R or Excel or something like that, to calculate both the chi-squared test statistic as well as the p-value. Usually does it in one go, right? So we would usually use software to calculate the chi-squared test statistic. Sorry, my desktop is just on the fritz. We've got a crazy snowstorm right now. Maybe that doesn't affect my desktop, but feels like it. We would usually use software to calculate the chi-squared test statistic as well as the p-value. But to calculate the p-value by hand, we need a chi-squared table, right? And so by hand. Of course, you can look up, an online calculator or something like that. But I will say that for the assignment questions, it's probably going to be assuming, or it is assuming that you're using the tables. So it's set to allow for a little bit of wiggle room, but it is assuming that you're using the tables. Okay, so to find the p-value by hand, we need a chi-squared table. We need to use a chi-squared table. Can't remember if oh yeah, because my computer was acting up, but so I don't think I posted it, but it is at the very end of the textbook. So it's available in the back of the textbook. Or posted on Moodle, but I don't think I had a chance to post it because I was struggling to even get on into our Zoom room. So available in the back of the textbook or posted on Moodle. I have it here. That's where I got it from. But so the chi-squared table, what's nice about, and I haven't really looked at the distribution tables, so the probability tables, the Z tables, eventually the T tables, the chi-squared tables that are in the textbook, is that they do have, about a page or two where they go through and they talk about how do you use the table and stuff like that. So I included that here, but really what we need is this here. This is our table, and maybe I can nab this. Let's see if I can grab this here. Should have put this on like page 50 or something. Okay. So here is the chi-squared table. This is the chi-squared probability distribution table. So if we look at this table, we see that we need the degrees of freedom. So the degrees of freedom are going to be increasing from 1, and eventually it'll start skipping around here. But we've got pretty good coverage from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Which means we know everything for up to 21 groups. It seems unnecessary to know more than that, right? But then it gives us for 25, 30, 40, 50, right? If you had, for some reason, more than 50 groups, you would have to use 50, okay? And so here, what I want to say is that you always round down to oh, hello. Yes, question? Maybe not. Okay. You always round down to the nearest degrees of freedom. Right, so for example, if you find that you have 39 degrees of freedom, then you would use 30, Okay, and that's always going to be the case with 30 with the degrees of freedom, is you always round down. If you don't have the exact degrees of freedom, then you always round down, right? So if, for example, the degrees of freedom is 40 minus 1, which is 39, we have to round down and use 30 degrees of freedom if we're using the table. We must round down and use degrees of freedom equal to 30, right? If we are using the table. Okay, so that's really important, because otherwise you're assuming that you have more categories than you actually do, right? So it's better to assume that you have fewer categories and go from there. And same thing later, it's going to hinge on the sample size, and then it's going to be more obvious. Okay, so most of the time, we're not going to have more than 6 categories, right? And so here, right, most of the time, we will have less than 6 categories. Right? Seems weird to have a huge number of categories that we want to analyze. We can, right? But most of the time we're up, we have, you know, between 1 and 5 degrees of freedom. 2 categories is a little bit weird, because then you could just look at one category and analyze it as if it's one sample proportion. But I mean, I guess you can. Okay. Usually we're going to talk about 2 degrees of freedom, 3 degrees of freedom, right? Because then we have 3 groups, 4 groups, 5 groups, 6 groups, right? And so another thing that I want to mention here is, if we have degrees of freedom equal to 1, we only have 2 groups or 2 categories. In that case, we could just use a 1 sample proportion, right? Remember the video I posted, half do or half don't? Well, it's both, right? So then if you only have 2 categories, right, half do and half don't, you could just analyze the one of them, right? So if we have degrees of freedom equal to 1, we only have 2 categories, which means we can use a 1 sample, or a 1 sample proportion to test the hypothesis, right? And so for us, we're going to focus on 2, 3, 4, 5 degrees of freedom. Now, you're just going to have this table, you're going to have it available. And so we need to just be able to read it, right? And so what happens is, if we say that we have 3 degrees of freedom, for example, or maybe let's do 2 degrees of freedom. We have 3 categories, right, in that kind of fake example that we started with. So with 3 categories, we have 2 degrees of freedom, right? And so what these cutoffs are saying is that as we move from 0, okay, so up to 2.41, the upper tail probability, so the area in the upper tail, becomes 0.3, right? At 3.22, the area in the tail is 0.2. At 4.61, the area in the tail is 0.1, okay? At 5.99, the area in the tail is 0.05. So notice how we're working our way through here. And I wonder if we have, B, 2 degrees of freedom. Something like this. So if we have degrees of freedom equal to 2, okay, then we can grab that degrees of freedom equal to 2 from the table. Let me just bring it in here. How about there? Okay. So then what we're going to see is that, okay, with 2 degrees of freedom at 2.41, then the area in the tail is 0.30, or they don't have the trailing 0, but that's okay. So 0.3, and then at 3.22, the area in the tail is smaller, makes sense. 0.2. Okay. 4.61, that's the area that's been shaded, I think. Right. So here, 4.61, the area in the tail is 0.1. Once we reach 5.99, the area in the tail is 0.05. So remember, when we're finding our p-value and we're doing our conclusion, a p-value less than the alpha level, and the default alpha level is 0.05, right? And so a p-value that's less than 0.05 means we have enough evidence to reject H0. Now we're going to start to think of it as, and we've always been able to think of it this way. We can always find a threshold where we would reject H0. And so here, what we're going to have is we're going to have, let's do this. If alpha is 0.05, okay, we see that we would reject H0. Right? When do we reject H0? When the p-value is less than the alpha level. And here, because we're moving out further and further out into the tails, right, then the p-value would be less than 0.05. So if the alpha is 0.05 and the degrees of freedom is 2, and df equals 2, we would reject H0 if the chi-squared is larger than 5.99. We would reject H0 if chi-squared is greater than 5.99. Okay. This is what we call the critical value approach, right? And so now when we're comparing our chi-squared value that we calculated to some value 5.99, which we found in the table, right? Then we call that the critical value approach. Critical value approach. Okay. We could have just as well used this table, and we could, so the other way that we could do it is we could say, well, if I find a chi-squared that's somewhere between 4.61 and 5.99, then I know that my p-value is somewhere between 0.05 and 0.1, right? That can be a little bit confusing if you want to talk about it that way, right? So, or the p-value approach, oops, would say that, okay, here, copy, paste. If the calculated p, right? Or maybe what I'll say, I'll explain what it does instead, right? So if we have 2 degrees of freedom, right, with 2 degrees of freedom, find the values that wrap around your calculated chi-squared. Okay, so find the values that wrap around your calculated chi-squared. Okay, to find the p-values that are associated with those 2 values. So then find the values, or sorry, the p-values associated with those values. Oh, so many values. Values. Okay. Here, right, you're doing the same thing. You only need to do one of these, and this is the same. So this, we're going to carry this through into when we analyze the means. Okay, and so pick a way that you like, and I am going to try to illustrate as often as possible. I'll try to illustrate both. Okay, because the p-value approach is a little bit harder, I tend to do that one just so you can see it, because this one, it's a little bit easy. So I don't want to show you the easy way and then you have no idea what to do with the hard way. So I like to use the hard way to show you, but then if you like this, the critical value approach, that's totally fine too. Right, and so for test 2, you're going to have to submit your work. Okay, and so then I'm just reading your work, and I'll follow as long as you explain clearly what you're doing, right? Okay, so the conclusion stays the same. That's what's really nice about hypothesis testing, is that once you have a p-value, right, or in this case, right, if you have a chi-squared that's greater than your 5.99, in this case with 2 degrees of freedom, that would change, right, if you have different degrees of freedom. But let's see here. So if you have a chi-squared that's larger, so past this 5.99, the critical value, we call it, we could also, in the rejection region, right? So here we would call this the rejection region, but I don't want to overload you guys. So if the critical value, or if your test statistic is beyond the critical value, is larger than the critical value, then you have enough evidence to reject H0. Or if the range of your p-values is less than 0.05, then you have enough evidence to reject H0. Yeah. So step 4 is the conclusion. I feel like I bumped it down so far, but whatever. So we've got 2, so we can use the critical value approach, or I'll put it in quotes, the p-value approach. Okay, so from step 3, we could either use the critical value approach or the p-value approach. You only need to pick one of these, right? Pick one. But you've got options now. And we could have done the same thing, but you can see how it would be a lot in chapter, or earlier in chapter 6, right? Because we had Z scores. So what we could have done is we could have said, okay, if I have a Z that's larger than 1.96, I am going to reject H naught, right? It kind of makes it tricky with one-sided and two-sided tests, right? Because then it might not be 1.96. So I don't like to introduce it there, but I like to introduce it here, okay? Because I actually think the critical value approach is a little bit easier. So here, what we would say is if the calculated chi-squared is larger than the critical value found in the table, we have enough evidence to reject H naught. We have enough evidence to reject H naught. Okay. If we're using the p-value approach, then what we're going to have is we're going to have our calculated chi-squared. It's going to fall between some chi-squareds in the table, right? And then if the range of the p-values is less than the alpha level, and I'm going to say it here, I say it a ton, and then I know I'm going to have questions. What if I don't have the alpha level? What do I use? 0.05, right? So the default is alpha is 0.05. Okay, so if the range of the p-values is less than the alpha level, which is a default of 0.05, we have enough evidence. We have enough evidence to reject H naught. Okay. So depending on how you tackled step 3, right? You only have to pick one of these, then that's going to determine how you find your, if you have enough evidence to reject H naught, or if you do not have enough evidence to reject H naught. Oops. There. But then once you've either rejected H naught or you fail to reject H naught, then you state the conclusion in terms of the question. So then state the conclusion in terms of the question. Okay. Good. All right. So I think we're ready for an example. Maybe I'll put it on a fresh page. Okay. So we're going to start working through this, but I see that I'm a little low on time and I don't think we're going to make it through all the way. But what I want you to do is whatever we don't finish of this question, I want you to work on your own, right? And then we'll finish it on Wednesday. So I'll make a note here. Whatever we do not finish of the following example, do on your own, and we will finish it next day. I can't remember, Thursday. Maybe I'll just say next day. Okay. All right. So a professor using an open source introductory statistics book, that's us, right? You've got a free textbook. I hope you're using it. It's a really good textbook. They've put a lot of work into it and they explain things really clearly, I think. So I'm always, I'm impressed with how clearly they explain things. Like, wow, nice. The older editions were not as clear. And so this one, I'm really enjoying this version of the textbook. So a professor using an open source introductory statistics book predicts that 60% of the students will purchase a hard copy of the book, 25% will print it out from the web, and 15% will read it online. I would guess that in our class, pretty well everyone's reading online, and sometimes I'll have some students who print it off the web, but we don't live in the States, so it's a little bit tricky to buy a hard copy. I think you can, but they charge a lot of money. Anyways, at the end of the semester, he asks his students to complete a survey where they indicated what format of the book they used. Okay, so if you think about so we're going to have expected counts, and then we're going to have observed counts, right? And so now when we talk about 60% will purchase a hard copy, 25% will print it out from the web, and 15% will read it out, will read it online. That's 3 categories, right? And so now, right, I have this expected distribution among those 3 categories, right? And then now at the end of the semester, we actually ask them, okay, so what did you guys do? Right. And so of the 126 students, so we've got a total sample size of 126, 71 said they bought a hard copy of the book, 30 said they printed it out from the web, and 25 said that they read it online. Okay. First, we're going to state the hypotheses for testing if the professor's predictions were inaccurate. Okay. And so here, what's tricky and like what I don't like about chi-squared is there's no exactly right hypothesis, but the null hypothesis always has to be that, okay, we assume that our sample is the same as the expected distribution. Okay, and so for part A, our null hypothesis is going to be something along the lines of the professor's predictions were accurate, or let's say the predictions of 60%, 25%, and 15% were accurate. The predictions of 60%, 25%, and 15% were accurate. Okay. Whereas the alternative hypothesis is that the predictions were inaccurate. Okay. There's a lot of wiggle room here, right? You could have said the predictions were accurate, but I chose to kind of illustrate with the actual predictions. You don't have to do that, right? And so here it's kind of open to a little bit of interpretation, right? And so as long as you're saying, okay, the distribution in the sample is the same or is not statistically different from the hypothesized distribution, then you're good. Okay. So in terms of the information that we have, we're going to set it up in a table. Okay. And so for part B, it says, how many students did the professor expect to buy the book, print the book, and read the book exclusively online? And so here we're asked to find the expected, but let's just go ahead and make a little table because I find that that's the easiest way to summarize this information. Okay, and so I'll make a note here. It asks for expected values. but we will organize an entire table. To simplify our calculations later. Okay. So if we have some categories, all right, let's break this up here. I'm going to have some observed, and then I'm going to have some expected. Right. Helps if we have kind of some framework, some default framework to work with here. So you're always going to start your table like this. And then what we're going to do, so you have some observed and some expected. Okay. And we have three categories, right? We have the hard copy. We have the print, right? They're going to purchase a hard copy of the book. They're either going to print it off from the web. So then kind of gets weird, but I'll call it print, and then online. Hard copy, print, and online. Okay. So from the question, we know how many bought a hard copy, how many out of 126, I want to say. And maybe I'll bump this over just a little bit so I can fit a total at the very end. Okay. The total for both of these should be 126. Okay. So first, these ones are easy, right? The observed, because we just grabbed those from the question. 71 said they bought a hard copy, 30 said they printed it out from the web, and 25 said they read it online. So here, just underline where I got it from, I think. 71, 30 and 25. It never hurts to just double check your counts, right? 71 plus 30 plus 25, it is 126, so that's good. Okay, so now what we can do is we can use this 126. So if I had 126 students and I told you that I'm expecting 60% of those 126 to buy a hard copy, then what am I doing? Well, I'm taking the 60% of the students, which is of the 126. So I'm going to take 126 times 0.6. I expect 75.6 students, and we're allowed to have we're allowed decimals in expected values. That seems weird, right? Because we can't actually have 0.6 of a person buy a hard copy, but we can expect 75.6 people. Okay. So what I want to do here, well, before I let you go, right, this is going to be 126 times 0.60 is this. Okay. So I'm going to let you finish this table, work through the rest of the problem, and it is going to be the first time that you're working through a chi-squared and using a chi-squared table, but we've talked about it. Now it's time to apply it. All right, so finish that question up for next day, and this is where we'll pick up. And if you have any questions, let me know. Otherwise, I'll see you on Thursday.